Hello everyone, my name is Yuzi Zhang. I'm from University of Pittsburgh. My project name is Transport Properties of Non-Reciprocal One-Dimensional Quantum Channels at LEO-STO Interface. And these are conceptual figures of the work on this interface. We just write a device and we want to do some experiment on it to do some research. So for this interface, it shows many interesting properties. Firstly, we all know that only if it is a titanium oxide terminated interface, it could be conducting. And then when we add positive or negative voltage, it could be tuned between mantle and the insulator. And also, if we give a different magnet, it could tune the critical point of the temperature of superconductivity. So for this material, we want to do some furthermore research. So we use atomic force microscope lithography technique. We use this to do a quantum simulation on this interface, and that if we add a positive voltage to the tip, we could write some wires and some virtual electrodes, and also the main channel that can help us to have a base of the conducting area. And then if we add a negative voltage, we could get a barrier. It can also help us to block the conducting. So, and also for this simulation, its resolution about 2 nanometer, so it still has a limit. So these are formal works that after we write a device and research on these properties, and we find out that some interesting properties such as that the electron will guide, we could see some quantized conductance and some rich subbands in transconductance picture. And also we can see the single electron transistor that the moving electron could add one by one, and then it shows the quantized conductance. And also we find that the electron pairing without superconductivity, and also the electron and electron interactions could be tuned when it came to potential could be different. And to furthermore knowing more about the writing of our device, we use some specific parameters. They are empirical. So for the main channel, the length is about 1 micrometer, and for the barrier, it is highly transparent potential barriers, and its length is about 10 nanometers, which makes sure that they could be tuned by the side and back gate. And for the side gate, it actually tuned the chemical potential. And then when we cooling down this device under low temperature in device, maybe about 20 or 50 millikelvin. It shows some interesting electronic properties, just under condensation of the conductance, and also the transconductance shows some rich subband structures. To explore more about the subband structure, we use vertical lateral modes, and it could be plus with spin, and it shows many more interesting things. Yeah, so that's the framework of these one-dimensional electron waveguides. Firstly, without modulation, it's a straight waveguide. And then if we want to get a lateral modulation, we will just trace the FM tip with a sinusoidal path. And if we want to get a vertical modulation, we just modulate the amplitude of the tip voltage to get it higher and lower, and also like the sinusoidal. Then if we want to combine these two things, we could get helical modulation, and we can see it has chiral properties. So for this four modulation, we could see some difference between them in conductance and transconductance figures. Especially for the helical sublattice device, we could see there's oscillation of the conductance at the plateau of the quantized conductance. It's very interesting because it could be influenced by the spin orbital interaction magnet, which combined with the magnet we given, and the effective magnet is in this direction. So for the chiral, molecular, and spin polarized transport, it has some interesting effect that this chiral-induced spin selectivity could cause the reduction of elastic backscattering in electron transfers to chiral moleculars. So we also want to know if this could also happen in RL-STL interface. So we do the framework, and also this my work also want to give a chiral waveguide. This waveguide we combine sine wave and two inverted quarter arcs into a chiral waveguide unit, and then we repeat it several times to form this chiral sublattice, and then we want to know much more about its electronic properties. This is still on progress. So for summary, we develop a nanoscale platform and engineer some one-dimensional quantum wires to do some measurement to know some electronic properties of this materials, and we could see the quantized ballistic transport, and also in the helical modulation we could see some oscillation transport behaviors which engineered by spin-orbit interaction, we think. And these experiments represent the first step towards engineering property in one-dimensional quantum wires, and also it could be regarded as a building block for more complex quantum systems.